I've told you that whenever you have a dynamical system, you should immediately look for Poincare section. Usually finding a Poincare section is a dark art. You do this, that, and try to make it transverse. But in billiards, they're very beautiful because Poincare section is unique and obvious. I mean, maybe not unique, but there is one Poincare section that's obvious. There is a wall of the billiard, so that we can parameterize by some length S, let's say, because it's usually some curvilinear wall, so there's a length. And at the point of impact, I have parallel momentum, which I'll just call P then. And because the velocity of vector is 1, I know what the transverse momentum is. So I have to specify only one component of the momentum. So the Poincare section is two-dimensional. And in this particular case, I can try to draw it in 3 dimensions. I can draw it like some kind of cylinder. Or in this dimension, we move along the perimeter, and in this dimension, we move along the parallel momentum, P. And the way that I've constructed my problem by setting velocity equal to 1, mass equal to 1, that goes from 1, minus 1 to 1. So in this case, Poincare section is a connected two-dimensional, you could make it a cylinder if you want to, you could draw it, in which one direction you move, you measure the length, meaning where you are. So for example, this point here is someplace over there. But this point has outgoing momentum that's pointing in an opposite direction than the direction of the boundary. So this point is on the back wall, someplace behind. Well, if I send the ball out this way, someplace here on the front sheet. Can you visualize that? Yeah, so the section is a two-dimensional surface of the cylinder, and if we know where we started, and we know the parallel momentum, we know the two-dimensional velocity, and from that we know entire orbit. If we started, that's unique specification. So even though the billiard is in 4-dimensional phase space, there is a natural Poincare section in which dynamics is extremely simple. So now the Poincare map dynamics looks something like that. I start here, and I just move until I hit the wall again. So that will happen. I start here, and next time, so this is my S, and why did you let me do this? Okay. So while I'm bouncing in this space, I also move on Poincare section, and every time I hit the wall, I record it where it is. So, I start here, and my dynamical systems map F going one step forward, Poincare section coordinate parallel momentum. So, position. The vertical axis is the parallel momentum, and I draw the weird shape because I I just put the, out of the board, I put the second coordinate, and then I turn a little bit sideways for your pleasure to watch it. Yeah, so if I have a collision like this, a grazing collision, then P equals 1. If I have a normal collision, I come in and come out. So normal collisions would be on this line. The grazing collisions would be at the two edges, depending whether I'm going this way or the other way. Of course, when we really do this, we don't draw this picture, but we actually just draw a rectangle which has coordinate s going from 0 to the length of the perimeter. So this is length, if you wish. L is the length of the perimeter. And here we have minus 1 to 1 for the parallel momentum. So we just draw it as a little rectangle. And then we study the dynamics. Instead of looking at the billiard, we study just how the points hop around here. Now you don't appreciate it, but if you run this billiard, so by the way, I gave you an exercise which is, writing the simulation for this billiard. Now I don't mind if you don't do it because, it's okay. I mean, for us it's a conceptual tool, this billiard, we really will not be predicting important things with it. So there are few packages that work, on Chaos Book Extra, so use that if it makes you happy, or draw it by hand, but it's not very hard to code it, so maybe you just want to code it anyhow. But it's very instructive. And the point will be that you don't appreciate it now, but if I look down, as I play pool, if I look down on the table, this will be arbitrarily complicated. I take any trajectory, just going to go all over the place. It's going to be really hard to figure anything out with this trajectory. Why? Because it's a four-dimensional phase space, and you're being done. You're looking at a projection of the four-dimensional thing in some arbitrary plane. To you it seems very natural because you chose these coordinates to be your table. But actually, you can't figure anything out. Now, when you do it on Poincare section, you will be only studying transverse motion of the billiard, something that you can visualize here. And you will see stable, unstable manifold. Your Jacobians will give you lots of information, and you will actually see what's going on. So going from this representation, which is very intuitive, if you play pool, to a Poincare section representation will turn out to be very powerful. How would a smart high school student put this on a computer? I say high school because it really requires nothing than Euclidean geometry. And sweeter still, we'll be able to write analytic formulas for Jacobians, and they'll be very intuitive. So there's one system in which, and we'll be even able to compute stability of periodic orbits analytically for a few orbits. And I'm actually very proud of this because I had a collaborator that produced 1,000 orbits, and I analytically computed the third one, and he was wrong at 1% level. Now, in this class, we expect you to be good to machine precision. This is deterministic chaos. So he had to shave his head in shame. No, he didn't, because he's a modern German. He has no pride, but he fixed his program and everything worked. So, it's wonderful to have kind of analytic thing at hand when you can have it. Unfortunately, it's so rare, but this is one case we can do it. So let me now draw a picture. Which in the old days, we actually still have that thing, but nobody is using it. We used to show overhead transparencies. We don't do this anymore, but it's much more beautiful than what I'll draw. So here I'll draw. We'll specialize now on the following problem. We'll put few disks in a plane, and we'll be so lazy we'll only use 3. If you use infinitely many, that's called Lorentz gas, and it's a very useful thing in statistical mechanics. If it's 3, it's just, when you have a pinball machine and you send balls from here, then at the top there are 3 disks, and they're doing chaos for you, randomizing on dynamics. And in the movie I'll put beautiful paintings of these pinball machines. If you don't believe me, that's what they look like. And we'll take very small point, infinitesimal. Turns out it's not crucial, but the only thing that matters is a circular elastic scattering, and it cannot gain angular momentum. So the only energy is just in the motion. And we'll get started someplace. And what this thing will do is, like in any pinball game, it'll bounce maybe a few times, and we're very good, then it'll fall apart, it'll fly out. And I'll use this to explain everything about how you think about chaotic dynamics. So this is a typical pinball game. Now, if you're a very good player, you might aim it in such a way it bounces a few more times. But it pretty soon turns out that if you want to control 10 bounces in the future, you have to have your initial condition specified to 1 Fermi or something, to subnuclear distances. So it's not going to work unless you cheat. That's called control theory. You can do this. As the pinball wizards do, they actually move the table as they play. But we're not allowed to cheat. So what I want to describe now is how I depart from here and how I depart from the next disk. And that turns is kind of very elementary geometry. So here am I on one disk. And then some other time, I'll make it really big. So in early Renaissance Italy, there was a competition for who will paint the Duomo in Florence, the cathedral. And competitors came with beautiful pictures of Madonna, etc. But Giotto, he came and he drew a circle by freehand for the jury, and they picked him, and they did very well. Now I'm not Giotto, but here we are. This is a circle. So this disk is impenetrable, has a reflecting circular wall. I'm doing this to test the video system and also Kimberly's auditory system. So I shoot out a particle. And I do this at a position s minus 1. So at time I'm here on the perimeter. This is s. And I do this with uniform velocity v n minus 1. So that's a vector. In our well, it's a unit vector. What it does, it reflects here, and to see how it reflects, I have to write the line that connects the center of the disk at time n. That's a symmetry line. And it exits at the specularly at the same angle. And that's Vn plus 1. And it hits the disk at the point S. No, this is just the end, Sn. So now I want to explain how you compute this position and this velocity if you're given your starting point and the center of the next disk. So usually the billiard is described, you just specify coordinates of the disk and their radii, and that's how you specify the billiard, the pinball kind of billiard, like this one. And the beauty of this simple problem is this is specified, a line is a linear problem and a circle is quadratic problem. And it turns out to evaluate this point, we'll only have to take square root once, and that's all. Everything is elementary. We don't even have to compute the sine or cosine or anything with trigonometric functions. And if you look at competing books, they're full of sines of cosines, etc. So you will, they never tell you that you don't actually need any of this thing. It's totally elementary geometry. So if I know where I am, I know where the center of next disk is, I know this vector. I'll call it D. And let's try -1. So this I know. Now, what I also know is I know the vector that's normal to this line. And this vector has a name that you must have seen. It's called impact parameter. So in scattering problems in electromagnetism and quantum mechanics, this tells you how big the scatterer is. Usually it's some potential, but here is a very literal quantity. The disk has a radius, and if your line goes outside, you don't see there is a disk, and if the line is closer than impact parameter. And there is the radius of the disk. I'll call this A n. And the disk is defined by a point on the disk, for example, this point here. So now, in four-dimensional phase space, this is a two-dimensional configuration vector n -1. In our Poincare section, it's specified by S n -1. But and this is, let me just write X, the next point in 4 dimensions. So what is this has to satisfy? It has to satisfy that X n minus the center of the nth disk, because I'll continue doing this, squared is the radius of the disk square. So first thing we have to figure out, am I going to hit the disk? To do this, I can construct, I'll rotate and at the velocity at n minus 1 by 90 degrees. And I'll construct a vector u, and 90 degrees in a plane is very simple. You just exchange x and y. So construct a thing that has components v minus 2. So this is by construction normal to that. Then I can compute the parameter distance as Bn equals so the distance along here as a product of this thing times u n minus 1. This by construction is a unit vector because v was a unit vector. So that gives me this distance. Now, everything I write might be wrong, right? So I expect you to keep me honest. So collision happens if and this is right angle, so I can define this thing here. This vector.